I am Saroja Kanchi from Kettering University in the Department of Computer Science at Kettering University in Michigan. And I have been working in the area of graph theory for a couple of decades now. And I have worked in topological graph theory. Then I worked on localization of networks, which is graph-based. And recently I got interested in graph neural network and its applications. So I wanted to provide the current status of the field and then show you some results that we have received. So I want to introduce the idea of learning and graph theory and why is it a challenge to learn from large graphs and how we can use encoder-decoder approach and then move on to constructing message passing neural networks for graphs. So I'll start with introduction to graph data and then the fact that it's prevalent now everywhere. And then we talk about what are the tasks that we're interested in relation to graphs. And then we'll talk about how is it that it's different to give a graph input versus any other type of input, such as images or such as, tabular data for a machine learning algorithm. And then we'll start with the encoder-decoder approach and move into graph neural network. So first of all, we all know that data explosion has been occurring over the last few decades, and it's phenomenal. The kinds of data sets that we have are extremely huge. And in graphs, especially with the creation of Facebook and Twitter and all the communication mechanisms with social media, we have graph type of data in very huge quantities. So there's been a dramatic increase in graph structured data. And earlier, before the machine learning techniques, graphs were actually treated with parallel distributed algorithms, parallel algorithms, sequential algorithms, with, which all take a longer time. They have a huge time complexity. And now, given the size of the graph, it is not possible to run those algorithms anymore. And we need to come up with easy and a better way of dealing with large graphs, really with millions of nodes. So examples would be including social networks, food webs, etc. So recently, ACM last year carried that the future is going to be big graphs, and one needs to work on how to create these graph processing systems that can work on large graphs using machine learning and AI, and that will be the future challenge for the community of predictions and AI usage of AI in the future. As some examples here is social network graph on the left. And then you can see some sort of a Amazon or technique recommender system on the right, where you have each node. If you think of it as a graph, each node then on the right has a person trying to shop using Amazon cart, and then you have different types of links saying whether they clicked on the product or whether they collected the product, whether they actually threw it into the cart or actually they bought the product. So the idea is to recommend products to the users. And of course, as you can see, the action also may depend on where they're located. If the person is located in Beijing or Bangalore or Boston, exactly what are they interested in? So how do we assimilate millions of nodes of this type and try to make a recommender system where we can recommend products to users in very short period of time, almost in real time? The second set of data we'll look at is biological data, where you have molecules. When you put some sort of a catalyst on it, after some time they go into a relaxed state. And actually to predict what the relaxed state would be, one has to do DFT computation, discrete Fourier transforms, which takes days. Is it possible to use machine learning, providing the initial state, which is a graph, and then end up with a relaxed state, which is also a graph. So we can then be able to predict the relaxed state very quickly. So those were just some touching upon important aspects of why graphs are everywhere and how now we'll talk about, notice that the graphs have started to change. Earlier, we used to only work with simple graphs, multi-graphs, edges or weights or not. But now we are seeing that multi-relational graphs of large sizes where edges can be of different types. So what are the graph related tasks that one is interested in? Node classification is the most popular one. We can think of things like Reddit data with blog posts, chat rooms. We want to find out what topic is it that's being discussed on a post. And then you could talk about links as people, maybe the link could indicate two posts that are commented by the same user. Similarly, PubMed is a very standard data for graph processing from CiteSeer and Quora and PubMed, where you talk about two papers being related to one another. if they cite one another. Using the citation links, can we then predict the topic of a paper? So some of the node classification techniques right there. The link prediction is another very important work in graph processing. Is for example, you have a Facebook friend list, which is a very huge graph. We want to talk about what is if the current time, for example, Adam and Maria are friends, Sophia and Maya are friends. In the future, in the time t+1, who are going to be predicted friends, which might again have to do with commercial marketing of products, etc., to a set of friends that are interested in the same subject. So this would be link prediction. And finally, the entirety of graph itself may be classified or may be regressed. For example, we can talk about graph classification as predicting the toxicity of a molecule, or we could talk about the level of toxicity, which would be a regression problem in graphs. So having motivated that graphs are everywhere around us, and these problems are extremely important, and traditional techniques of graphs do not seem to lend themselves to large graphs easily at all. So how do we then start using machine learning, in particular neural networks, for inputting graphs? One of the biggest challenges we have is that if you look at an image, every pixel have the same qualities. Whereas in a graph, a node is completely different from another node. A node's value depends on how it's connected to other nodes. A node's place in a graph is not only indicated by the node itself, but it's also indicated by what are its neighbors and what role does it play in the graph. It is therefore, when you feed an image, you're feeding a bunch of pixels. They all have equal properties, and then you feed in the next image, and you have a set of pixels that have same property. And so things like Euclidean distance between images are well defined. However, in a graph, it's not possible to use the same kind of techniques. So that is the first challenge that we have, is how do you create a learning mechanism for graphs? There are some techniques that have been tried, which we will talk about. So the first thing I want to talk about is what are some of the node features data that we can provide. Then we can run through traditional machine learning algorithm. And we'll find out that that is not, while it's important to understand node embeddings, but traditional machine learning algorithms don't perform very well because we are not able to provide the structure of the graph to the learning algorithm. So some of the properties of nodes one can list and provide, they have to be permutation invariant, which means it should not depend on the order in which we are processing the neighbors. An example of a node permutation invariant data would be a degree of a node. So you could add up all the neighbors of a node, and that would be one of the measures you could provide. Centrality measures are extremely important for graphs. Closeness centrality, bitweenness centrality, eigenvalue centralities are some of the centrality features of nodes one can provide to the machine learning algorithm to understand and predict nodes. Clustering coefficient is another good property of a node. Remember, it talks about how many different neighbors are connected to one another versus how many could be connected to one another. So how clustered are the neighbors of a node? Similarly, number of triangles around a node in the neighborhood of a node, and things like ego graphs and motifs, which are related to cycles and specific structures in the neighborhood of a node. So we're able to provide a number which is related to the node, which is invariant to the neighbors. That's one set of data we can provide about a node to a machine learning algorithm. Or we could provide information about links, and that's node-to-node information for links. Similarity matrix, how many neighbors you and V have in common. If you and V are two vertices of a graph, that could be a similarity of two nodes that could be provided. And that can be used for link prediction. So you're saying two things are connected to one another with the probability of one, if it will be proportional to the similarity, that is number of nodes they have in common. It can be used for link prediction type of work. Extending the idea of similarity of nodes, several people have proposed various node-to-node local feature measures. Many of them are normalized, as you can see. Sorensen is normalized with the degree, and Jacquard's is normalized with the size of the union or the number of neighbors of U and V. And some of them are related to the degree itself alone, where as you can see with RA, which is called resource allocation for between V1 and V2, would be you would distribute the degree around U to the V1 and V2 link. So various node-to-node local features have been proposed. And CATS index is something that's most used for node-to-node feature, which talks about basically it's the number of paths between the vertices U and V with weights of beta to the I. So it's a weighted measure of the number of paths between two nodes. And that's a very popular measure between node-to-node, global measure. So these are the type of information one is able to provide, which are permutation invariant about a graph to a neural network or to logistic regression or to some form of machine learning algorithm. So this is the first technique, is where we learn about graph by providing invariant information, whether it is of each node, or it is of links, or it is of the entire graph itself. Once you go through that process, then you decide that it really hasn't captured the structure of the graph. All these node-to-node features and node features are useful, but still it does not capture exactly how the graph is structured, to which nodes is each node connected. That information is still not yet fed into the machine learning algorithm. So the next approach is encoder-decoder approach, which then tries to find a way by which you can actually take the information about a vertex and find an encoding called Z. And here you could use machine learning to develop the encoder, which we'll talk about in just a minute. And once you get an encoding in a lower dimension, then you would decode and try to match up with the original information in the graph. So there are two unknowns here, which are going to be learned by machine learning, which is encoder and decoder. So you start with information about vertices that you can provide, which is a vector. And you try to develop an encoder and develop a decoder, and then try to match up the results with a loss function, for instance. So here is a simple encoder. One can, we talk about shallow encoding and deep encoding, but in a simple encoder, you could assume that the encoding is just the vector V has been mapped to a d-dimensional vector. Each vertex V has been mapped to a d-dimensional vector, and that's the mapping you're trying to find. So that's a shallow encoding. A decoder, as we know, will take that encoding that is mapped to a lower dimension and then try to predict something about the graph. And then we can match up exactly what it predicted versus what happened in the original graph. In the simplest case, you can take two ZU and ZV, which is the encoding of U and V, and try to predict, is there an edge between them, or what is the edge weight? So if you have a few training nodes and training edges, then you'll be able to match up how good is the learning algorithm, which means how good is the decoder and encoder that you've created, and then go back and using the loss function, adjust the parameters. So here is the optimization of the decoder encoder, which then talks about the loss function. So you take the decoder result from the ZU and ZV, which then tells you the prediction of whether U and V are connected, for instance, and then compare it with your similarity matrix that we talked about earlier, which is a similarity measure between U and V. And then you try to optimize the loss function, which means you are trying to find the decoder and encoder parameters that would reduce or minimize the loss function. So this is an approach that's been tried, and here is some shallow decoder, which means decoder in itself has a complete formula, which means decoder is really not learned, encoder is learned in this case. And therefore the decoder is just Euclidean distance between the two ZU and ZV vectors. And the similarity measure you use it could be adjacency matrix or something like a SUV that's been defined. And the next few are inner product decoders. And using this decoder, again, the similarity measure is either adjacency matrix. And you see the loss function could be the usual loss function, which is Euclidean distance between the predicted value and the real value, original value. Or it could be the log that we usually use called cross entropy that is used in machine learning. Whereas in deep walk and node2vec, the type of decoder that's used and the similarity measure is used is based on probability. These are deterministic similarity measures and probabilistic similarity measures, which talks about how many different paths is V involved in starting at U if you take a random walk of length T. And that's really what the probability here is. If you take a random walk here with unlimited or infinite random paths, how many different ways in which V can occur given you start at U. Again, we're talking about the probability here. So the idea then is you start with an encoder, and then you get the Z, and then you do the decoder using this equation, and then you calculate your loss function. And once the loss function is there, then you're trying to optimize or reduce the loss function and trying to find the right encoder for it. So this approach has worked, of course, better than the original machine learning with logistic regression and simply providing information about nodes and links that we saw in the earlier version. However, it has a limitation because the decoder and encoder don't talk to each other in any way. They don't share any parameters. And when you do shallow embedding, they do not leverage the node features of the encoder. So the question then is, how can we learn this embedding itself? Rather than us predicting the embedding and predicting the decoder, is there a way that we can learn, given a graph, we can learn the features of the graph themselves instead of trying to provide the features of the graph? And that is where the message passing system of neural network was created. Around 2016, it became popular. So again, I want to reemphasize how it is difficult to provide the graph data into a neural network, because each link, you simply cannot provide each link into the neural network, because each link has a different role to play within the graph. It's not like a single pixel or a table in an Excel sheet, whereas each row in an Excel sheet would have similar meaning or values. Here, each node has a different, and it's related to other nodes to it and what type of node it is, what links it has, and to whom it has links. So all of this has to be incorporated. And for that, we have a message passing GNN, which is called the message passing graph neural network. And the way this message passing neural network is going to work is that initially you collect node specific data. However you want to do that, we can talk about degree, we can talk about number of links it has, any information that we have about nodes, what type of node it is. So you create a vector here about the node, and the links are going to be processed in the neural network. Basically, the information from one node to another is then processed as these information is then fed to the neural network. Clearly, the number of hidden layers that we want to have is proportional to the number of path length that you want to process. In each case, you'll be processing one node to another. So when you go to the second layer, you're processing length 2 paths, and the third layer you're processing length 3 paths, etc. So basically, you can add as many message passing layers as you think is important in order to transmit information from one node to another node, how far you want to go in that. The number of hidden units within layer is proportional to the number of nodes in the graph, clearly. And then you provide this vector to each node. So this changed the way we process graphs into the neural network. Here is a very general description of graph neural networks with that picture that we saw. So the idea is that we start with the HU of 0, which is simply the X sub U, which is the vector at each node that we just talked about. Essentially, X sub U are these X1, X2, X3, etc. So we start that in the first layer for each node. And then in each iteration, in each layer, we actually update from the previous layer to the next layer. So in each iteration, we update the nodes information of the neural network at iteration k plus 1 using an update function and an aggregate function. So what the aggregate function does is essentially process the links. It says who are the neighbors of the node U, and it processes the current information at the kth iteration at the neighbors V of the node U in the neighborhood of U. Once you collect the information from the neighbors, then you add the information about the node itself. So the current message of the node along with the message of the neighbors is then updated using certain equation. So what the aggregate function is and what the update function is determines what type of graph neural network you get. And there are various things that have been tried for aggregating and various things that have been tried for updating. And the M is simply a notation for the aggregate. We call it the message collection information, which is really what it is. So M and aggregate are two interchangeable type of information. So when you go through all the K layers, capital K being the number of iterations, at the end of it, you have the embedding of the graph that you wish to obtain, which is Z of U, which is the encoding that we were trying to attempt in the encoder-decoder situation earlier. So here is the way the graphs are processed now with the graph neural network. you want to aggregate the information at A, you collect information from its neighbors, which are B, C, and D, which have already collected information from its neighbor earlier, and that's how we are processing two links here. And if you keep to the next layer, you'll keep processing links as you go, which is really message passing being the key for processing graphs, information from one message to the other. Now, we are making it real by actually giving some formula for the update and aggregate. There are many possibilities exist, but one possible aggregate and one possible update would be using a weight matrix essentially and summing them. So you use a weight matrix and you sum the information at your neighbors. And the bias terms, we're familiar with that. You have a bias term for the neural network, which you can ignore while writing the formula, but it's eventually needed when you implement it. Then you have the weight matrix for multiplying with the neighbors, and you have a weight matrix for the information at your own node. So processing at your own node and processing, and addition and sigma are the update values that we have decided. We're going to add the value at ourselves and at the neighbors, and then we're going to apply the sigma, which is really the ReLU or the tanh function that's standard for neural network computation. So with this, of course, the weight matrix are initialized at random, and then you learn, the weights are learned as you finally find the loss function. So here are some various ways of aggregation and various ways of updating, and gives you different neural networks, different graph neural networks that I talked about. In graph convolution network, essentially we are normalizing the neighbors' values with square root of the size of the neighbors. So essentially it's a normalized neighbor embedding. And we seem to keep the same type of weight matrix for both the node and the neighbors themselves. So, and also we have the same, tanh function right there for the sigma. So that would be Kipfen-Welling, which is the standard. That's how it started with 2016. Or you can run through the neighbors' values through a multi-layer perceptron and use with a parameter phi and another multi-layer, trainable perceptron for the aggregation and the update for the aggregation, and one for the weight matrix, and therefore you have a different message, which is multi-layer perceptron as an aggregator. Attention networks then gives attention weights, which are called attention weights, which are given weight to each. Attention weight is given at each of the nodes, and that's how now the weights are specific to each neighbor. So for each neighbor, the weight depends on the current node and the neighbor. Earlier, the weight simply depended on the set of neighbors. The weight matrix is the same, no matter who the U is. It depends on V, but right now it depends on both U and V for attention networks. And then we have gated graph neural networks, which is really recurrent update. So you're taking the current value of HU of k minus 1 and then running through the network in a recurrent fashion, which is basically recurrent neural networks adapted to graphs. Again, as I mentioned, after it goes through the various message passing layers and the number of iterations, then of course you have a prediction, then you would define the loss function, which you could use the cross entropy log function here with the negative logarithm, and that's very standard for neural networks, with a softmax function that's defined as, again, this is also a standard softmax function that's used, where yu is the predicted value by the neural network, that it belongs to the class yu. Now, or you could use a Euclidean loss function, which is the difference between the predicted value and the original value that we have for graph classification. So either way, once you get the loss function, then you go back and adjust the parameters, and the neural network proceeds with back propagation as expected. Now, we applied this for a couple of problems. One is the PubMed problem, which is the standard problem, which, as a proof of verification. Then now we've been trying the graph neural networks and various graphs of large size. And here are a few implementations. The first one that was tried was identifying low degree and high degree graphs. No information was given about any node. In fact, except, that absolutely nothing was given. The graph node was fed. And then we had two hidden layers, and the average accuracy was 77%. And here we used about, it was averaged over a node with 10 nodes to about 300 to 300 nodes at max. And we had accuracy of prediction of high nodes versus low nodes with 77%. The other very popular problem is finding cliques within a graph, cliques of size 5 or size n. Here we used a hidden layer of 5 layers. So we could process up to path lengths on 5, and we got an accuracy of 80%. Again, about 300 nodes were used to average, anywhere between 10 nodes, 300 nodes. Again, our training nodes were only about 5% in all of these implementations. So the idea is that the graph neural networks can be used for any graph problem now, since we can propagate information from one node to another. And depending on the type of problem, the interesting thing would be to find out which type of graph neural network would be more useful or more valuable for which type of graph problem. And finally, we had epoch versus training of test laws for the clique problem. And these are the results that we obtained in the early stages of. So that's what I had, and I'm now open to questions about graph neural networks or about the implementation.